Good morning. Continuous functions day two. Yesterday, what did we do? We were identifying whether a discontinuity was removable, infinite, if it was a domain issue, or what. They're all kind of domain issues, but the domain issues are more in the line of the value can't be used in the function at all, kind of like the square root ones here, or the square root one from yesterday. Today we're looking at a removable discontinuity, okay? Removing a discontinuity. How the heck do we remove a discontinuity? And removable discontinuities, basically what it is it's a hole, okay? And we're either gonna remove the hole or we're gonna fill the hole, however you wanna think about it, okay? So this question says define f of 2 so that f of x is continuous at x equals 2. And obviously I can see f of x equals x squared plus x minus 6 over x squared minus 6. And this whole define f of 2 so that f of x is continuous at x equals 2, it's kind of like the what? Well, basically what this is asking you is it's saying find where the hole in f of x, in the function f of x, is located and define it. Define what y value that hole needs to be to fill it is really what it is, okay? So we can figure this out really easy, and if we're at x equals 2, okay, just understand I'm plugging this in and I have 4 plus 2 minus 6 over 4 minus 4, and what I get is I get 0 over 0. 0 over 0 we know meant a hole, okay? So it's like when we're finding limits, we got 0 over 0 that said work a little bit harder, okay? So that's how we know it's a hole for sure, because we got 0 over 0. Well, because when I did that, I got 0 over 0, okay, we've been working on limits quite a bit. So the limits are actually going to help us find the value of that hole, okay? So we're going to kind of look at the limit as x approaches 2 of, and we want to find that hole, so what we're going to do is we're going to factor the top and say x plus 3 times x minus 2, right? And then the bottom is going to be x plus 2 times x minus 2. And what I'm going to do is we found that 0 over 0 is a hole, and we found where that little bugger is, so when we reduce that out, and then if we evaluate our limit there, well, now we have 5 over 4. Our limit's 5 over 4, right? So that's the whole value. So if they say define, okay, we're going to define it. Well, define f of 2, so f of x is continuous at 2. Well, if f of 2 actually equaled 5/4, I've just defined it, my function would be continuous at 2, okay? So basically what I'm doing is I'm removing that hole and I'm kind of redefining my f of x function as x plus 3 over x plus 2. And if that is my f of x function now, okay, I just redefined the entire function, the graph of this function and this function are identical to each other, okay? The only difference is f of 2 is defined over here, and it gives me 0 over 0 over here. So f of 2, when I find it, is defined as 5/4. So basically, this is what they are looking for. But what it does is it makes a whole new equation that is equal to, okay, these two equations right here, they agree everywhere except when x is 2. When x is 2 over here, I get 0 over 0. When x is 2 over here, I get 5/4, okay? So all I did was define the function. I defined f of 2 so that this function is continuous, and I could rewrite it as a piecewise if I wanted to, okay? So how about you give this one a try? Give it a hit pause quick. See if you can figure this out really quick, and I will do it for you. So define g of 4 so that g of x is continuous at 4. Okay, I'm back, and I'm going to do this with you. And just to see, when I plug 4 in, 4 squared gives me 16 minus 16 over 16 minus 12 minus 4. Yep, I get 0 over 0. Remember, that means whole. So in order to fill a hole, we're going to use our concept of a limit. We're going to take the limit as x actually approaches 4 of x plus 4 over x minus 4. And we know there's a common factor top and bottom, and I'm going to make 2 sets of parentheses here. I get x plus minus 4, 1. Doesn't matter the order in which you're going to write them. You're like, ooh, there's that pesky little hole. I'm going to get that pesky little fella out of there. And now I'm going to take the limit, and I'm going to get 8 over 5. So if I had to define g of 4, if it's defined as 8/5, if I define that value in that function, it is continuous at x equals 4. So that's what we're doing there, okay? Next problem, find a value of a so the given piecewise function is continuous for all reals. Okay, so we actually did this. This is similar to a problem we did a few note sheets before. We had to find an a value that made the limit exist, right? So we had to make sure the left limit equaled the right limit. Well, now we're doing a little bit more here. We're finding a value of a so that the given piecewise function is continuous for all real numbers, okay? Well, when I look at this, I can see that is a line, okay? That's a line. Lines are continuous everywhere. If I had a value for a, that would be a line, okay? Lines are continuous everywhere. The only place they might not be continuous is at this potential domain issue. And if you're like, what are you talking about, Kruger? What I did was I just made a graph quick, and I put 6 in there. So what this problem is trying to get us to picture, okay, it's a piecewise function. There could be a break in the graph. I need a value for a that is going to pull this graph down so there's no break in that graph anywhere. That's what it's asking me to do. Well, in order to find that, okay, I'm going to get rid of all this business here. In order to find that, right here is what I have to do. I have to figure out my continuity rules. My continuity rules are f of a has to exist. So when I plug that potential domain break, this is the only place it could be, is at 2. I need to find out f of 2, does it exist? Well, when I plug 2 in there, I have 2 times 2 is 4 plus 3. Yep, f of 2 equals 7. So f of 2, okay, it exists, it's 7, okay? Not only to that, because now we're talking about continuity rules, not only that, the limit of f has to exist. So what does that mean? Well, that means the limit as x approaches 2 from the right of f of x, that has to equal the limit as x approaching 2 from the left of f of x. That's what it means for the limit to exist, okay? Well, how did I do that? Well, what the heck? What the limit from the right side here, coming in from the right, because these are bigger, that's right side, that's left side. The limit from the right side, if I put 2 in there, what I have is I have 2x plus 1, and that has to equal my left-sided limit. Here's my left side, and when I plug that in there, I could go through all this math again, but I already found it when I plug it in as it's 7, okay? And Kruger, you really just kind of botched this here because we plugged 2 in for x, not a, so that should be a 2a, and then I just simply should be solving for a, okay? So I'm going to say 2a equals 6, a has to equal 3. So if a is 3, my limit exists, okay? So if a is 3, my limit exists, and if I come over here and I put a 3 in there, yep, 7 equals 7. And then the last one is right here. F of a has to equal the limit as x approaches a, as x approaches a, forgot to put that in there. but the limit as x approaches a has to equal. So I need all those to come together, and I can see if a is 3, my limit exists, and my limit is 7, because I can see coming in from the right, and f of 2 is 7. Therefore, if a is 3, it makes this function continuous. And just to show you that, if I came back to my graph, and I came here and I said tab, and I came up, and I came in here, we said if a is 3, my graph is going to come to, and look at that, it makes it nice and continuous, and I don't need to worry about this open dot here because right at 2 it's filled. So that makes it 2 continuous lines, and that's what that is asking me to do. That is a classic AP problem that they like to do. Okay, so now we're just going to take a little gander here at the second one, and f of x. Well, I'm gonna analyze this the same way. Okay. I need to be continuous everywhere. So the numerator, well, that's a parabola, so it's polynomial. They're continuous everywhere throughout their domain. This is a cubic. Those can wiggle and squiggle. X cubed minus 8. That's just a polynomial. They're continuous everywhere. The only place they may not be continuous is right here at -1. So what value for a would make this continuous? Now think about that a second, but be careful here. Be really careful here. Because remember, in order to find a value for a, okay, my continuity rules have to happen. F of a must exist, okay? The functional value at -1 is going to have to exist. If I look at this, what is f of -1 equal to? Which piece does -1 have to go into? The upper piece or the bottom piece? That's right. It does not go into any pieces because neither of these have an equal to on them. And because neither of those have an equal to on them, there is no value of a to make it continuous. Because f of -1 does not exist, okay? There's not one that'll do it. Now, if I modified this problem, just a skosh, I can do that really quick. Because some people are going to say, I didn't get enough examples, Mr. Kruger, I need more examples. If this problem were in there, and I slid, and I said, oh, f of a, now f of a is defined, okay? Now this 1, now it's in the domain of this function f. It's in one of the pieces. So then I'm going to look at this and I'm going to say, okay, what is f of -1? F of -1 is going to be -1 minus 8, right? So f of -1 is going to equal -9, okay? And I also need to make sure, so I just got rule number 1, and then I need to make sure that the limit as x approaches -1 from the left has to equal the limit as x approaches -1 from the right of f of x. Because if these two-sided limits are equal, that means the one-sided limit up here, that means the limit exists. If the left equals the right, it works. So I just got 1 to work by redefining my problem. That's not something you'll do in your book work. If they gave you that, there was no equal to on there, they're trying to trick you and saying, hey, you can't do it, and they want you to see that. But if it was on there, if that equal to were on there, now I need to make sure the left limit equals the right limit. So I'm going to de-junk this, and I just said, well, that's where the -1 is coming from. That's where my a value is coming from, okay? Or not where my a value, that's the only point that it could be discontinuous. And I'm going to switch that little guy in there, and if I'm looking less than 1, that would be the left side. Greater than or equal to -1, that would be the right side. So what I'm going to do is I'm going to come here and say, hey, what is my limit from the left? Well, my limit from the left is just putting a -1 in for all my x's, not that one. Okay, so if I did that, what do I come up with? Well, -1 squared is 1. negative 1 times 3, so that's going to be minus 3 plus a. That's going to be my left-handed limit. My right-handed limit coming in from the right, what's my right-handed? Well, that's plugging the negative 1 in there. That's my negative 9 that I figured out right away, so I'm just going to say negative 9. It's a crappy a. So I'm going to say negative 2 plus a would equal negative 9, so a would have to equal negative 7. If a, man, that's a bad a equals negative 7, it would be continuous, but notice that's when I changed it. So if a is negative 7, it's continuous, and I would be able to graph that piecewise function, and it would connect at that spot, okay? So then we're going to come on to a theorem of continuity. What does that mean? Well, the intermediate value theorem. I'm going to put a red star, a couple of them up here, because they are identified almost every free response AP exam I've ever seen. Students have to identify the intermediate value theorem, codenamed the IVT, okay, intermediate value theorem for continuous functions. It's a little mouthful when you read it. A function, y equals f of x, that is continuous on a closed interval. Let me rewrite. A function y equals f of x that is continuous on a closed interval, a to b, takes on every value between f of a and f of b. Okay? Now, some people are like, what? That doesn't make sense. Well, in calculus, you got to be able to read some theorems, and you got to be able to make sense of them. And if you don't make sense of them, I'm trying to simplify it for you. Okay? However, there's a couple important things here. Closed interval. Closed interval. What does closed interval mean? That means endpoints matter. The endpoints matter and they exist. Okay? They exist. That means I have no open circles on my endpoints. Because if I do have endpoints, open circles on my endpoints, I can't use the intermediate value theorem. It has to be a closed interval. And also, this, don't get wigged out by this AB, that is an interval of x always, okay? These are always going to be giving you intervals of x, okay? It says continuous, okay? So in order to use, this is fundamentally important, before I even explain it, in order to use the intermediate value theorem, I have to know two things. Okay, to use this theorem, your f of x function, number one, it has to be continuous on your closed interval. It has to be continuous on that particular closed interval. If it's not, this theorem is completely useless to you. Okay, but if it is, it's usable, and I promise you, you'll use it if you want to get full points on one of your problems at the end on a free response. Well, when I put it into a picture, I like to think of this as a common sense theorem, okay? Because it really is. F of A, that's just an F of B, those are just Y values. Okay, so all that means is if I come across, and let's say I don't care where A is. A and B, they can be any numbers. They can be positive, they can be negative. So all I'm going to do is I'm going to say, okay, here's A. And if I put A in, and let's say I get F of A down here, because that's a Y value, what that's doing is that's just giving me a point down here somewhere at A F of A. I'm not nearly low enough because it's going to kind of come across. That little rascal is going to be right about here. So that's the point, A comma F of A. It's just a little ordered pair. And when I put B in here, let's say it doesn't have to be, but this is going to be my F of B value. All it is it's an ordered pair. That one's going to be closed, okay? All this whole theorem says is that my endpoints, number one, have to be closed, and my function has to be continuous because if I connect it, it doesn't matter how I connect it. I can connect it with a line, I can connect it with a curve. I can connect it with a really wiggly, squiggly curve. It doesn't matter. But in order to get from f of a, from this point A to get to point B, it was continuous. I could not pick up my pencil. All this theorem means is it guarantees all values between this one and this one are taken on that function. Okay, that's the happy spot. What the heck do you mean? It means, let's say this is down at -8, and let's say this is up at 9. Okay, those are my y values. This is -8, this is 9. All it means is somewhere between f of a and b, somewhere between there will be a y value of, say, +1, because this is going to take on all values between f of a and f of b. So I'm going to put, I think, this between a and b, those are all happy places in there. All the values, all the y values between -8 and 9 will be taken on between this interval, okay? Hopefully that makes a little bit of sense, but you have to connect it with a continuous function. It's not telling me about the shape of the graph, okay? Because please understand, I could connect these points like this, but it is not guaranteeing me any of these values up here. It's not guaranteeing me any of those. I could connect it and I could go, whoa, whoa, like this. It's not guaranteeing me anything below here. It's just guaranteeing all values between f of a and f of b. The intermediate value theorem gives me all values between f of a and f of b are guaranteed. Okay, and they ask you these questions weird on the AP test, but we'll have practice tests for them. Okay, so for instance, if I said this y value were -8, this y value were 9, does there exist some x between a and b such that f of x equaled -2? Well, does -2 fall between -8 and 9? And if the answer to that question is yes, then the intermediate value theorem guarantees there's some value x that is going to spew out -2. And hopefully that makes a little sense. We're going to move on to the next one. Old AP test question. Okay, how would this be used? Well, this is multiple choice, non-calculator. The question stated f of x has exactly one positive root. Oh God, back into terminology. One positive root. Root, what is a root? A root is a 0 or an x-intercept. All a root is, remember, and that's the f of x equals 0, some y equaling 0. So f of x has exactly one positive root. On which interval below must the root for f of x occur? Well, all we got to do is we got to go through and test some stuff. So there's my function. Here's my function, f of x. So what is f of 0? F of 0 equals -1, right? Okay. What is f of 1? Well, f of 1 is going to be 1 minus 1 minus 1 minus 1, which equals -2. Well, if I go from -1 to -2, did I cross the x-axis? Did I cross the x-axis between here? I may have. I don't know the function. It's possible, but it's not guaranteed. Okay, so I'm going to move on to the next one. What is f of 2? F of 2 is going to be 8 minus 4 minus 2 minus 1, which gives me what? 6, 7, that gives me +1. Well, if I went from 1 to 2, if I went from -2 to positive 1, did I just cross the x-axis? Does 0 exist between negative 1 and 2? The answer to that question is yes. B is the answer. Okay? And I could keep going all the way between here because I know this one is f of 1 is going to output negative 2. F of 2 is going to output 1. 0 falls between there, so that's the interval. Over here, f of 0 was negative 1. F of 1 was negative 2. Okay, 0 does not exist between there. That's why I threw that out. And if I continued, f of 3, what is that? That's 27 minus 9 minus 3 minus 1, which that's going to give me 14. And I would be done on this question, but f of 2 is 1, f of 3 is 14. Does the number 0 exist between 1 and 14? No. Okay, it's not going to go between here either. It's only going to go between one of them, and that's how you would be using that. Last problem. Okay, this is the way your book is going to word it towards you for some homework problems. If f of x equals x cubed minus 3x squared minus 9x plus 5, verify that f of x equals 6 is on the interval from negative 1 to 3. Okay? So, does f of something equal negative 6? Well, let's check it out. What is f of negative 1? F of negative 1 is going to be negative 1 minus 3 plus 9 plus 5. So I'm going to say f of 1, well, what does that equal? I think it equals 10. Okay. What is f of 3? My other f of the left endpoint, f of the right endpoint, what does this equal? 27 minus 9 is 27 minus 27 plus 5, that equals negative 22. Okay, if f of negative 1 equals 10 and f of 3 equals negative 22, that means some number between negative 1 and 3. Does this fall between 10 and negative 22? And if the answer is yes, it exists by the intermediate value theorem. Okay? What did Kruger not do first? Which was very stupid of him. Okay? First thing, before I even think about doing any work, I need to know, is that function continuous? And it is a basic common knowledge question that we need. Parent graph, parent graph, parent graph. This is a polynomial. It is continuous everywhere. Okay? We don't have any vertical asymptotes. We could graph in Algebra 2 and Algebra 2 or pre-calc. I don't want to say Algebra 3. None of you guys took that. Polynomials and behaviors, they were wiggles and squiggles. You graphed them. They had no discontinuities anywhere. This interval is closed. I know via the brackets that are on it. Because it's continuous on a closed interval, the intermediate value theorem can be applied. Just because I have a function that may have discontinuities in it doesn't mean I can't use the intermediate value theorem, okay? If I said f of x equals 1 over x plus 2, but they gave me an interval from, say, 3 to 6, and they wanted to know if some f value fit, okay? The only discontinuity here, x cannot equal negative 2, because the discontinuity in that rational function is not in that interval. I would be able to use the intermediate value theorem on it. So regardless if the function, as long as the function does not have a discontinuity on the interval that they give you, you can use it. But if it does have a discontinuity in there, it does nothing for you, okay? If my function is not continuous, from point to point, this theorem is useless, okay? Just so you know. Any questions? Look me up, text me, email me. Hope you have a good rest of your day.